Hello, my name is Xiping Zhang. I am a PhD student at Yale University. Today, I will present our paper entitled Self-Annotation Methods for Aligning Implicit and Explicit Human Feedback in Human-Robot Interaction. Most prior work in robot learning in HRI focuses on using explicit human feedback. In this picture, the man is teaching the robot by giving an explicit reward value of +1. However, we can also see the man is naturally giving off facial reactions. Such implicit feedback in the form of nonverbal behavior can serve as a passive and burden-free information channel in human-robot interaction. Recent work in the field of robot learning has started to utilize the information from implicit feedback, yet their use of deep learning models can be extremely data demanding. Therefore, a critical question emerges: how do we efficiently get data for learning to map implicit feedback to explicit feedback? One common approach is to perform third-party annotations via crowdsourcing. However, we may wonder, what if the annotators are wrong, since they cannot read the mind of the interactants? Instead, we investigated self-annotation methods to align implicit and explicit human feedback by asking the same user who just interacted with the robot who labels data. We conducted a user study in which participants interacted with a robot photographer on a small tabletop platform with 4 degrees of freedom and a screen face. The robot can also speak to users. The robot sequentially completed photo-taking tasks with the participant, while we simultaneously recorded people's implicit reactions, shown in the video on the left, and the robot's behavior, shown in the video on the right. Then, we asked participants to annotate the videos of their interaction with the robot using ELAN, a well-established annotation tool for video recordings. Through the study, we investigated 2 research questions. First, how do different self-annotation procedures influence human perception of the annotation process? And second, how they influenced the usefulness of the data for mapping implicit signals to explicit measures of robot performance. Worth noting, we asked participants to annotate the videos of their interaction with the robot considering multiple performance dimensions. That is, for each of the high-level actions that the robot executed, users indicated how well the robot behaved in terms of its proficiency as a photographer, the social appropriateness of its behavior, and its entertainment value. We designed user study considering 2 variables in relation to the annotation process. The first variable was annotation order based on the 3 performance dimensions that I mentioned earlier. With the by-action order, the participants annotated all 3 dimensions of the robot performance together for a single robot action at a time, and then they proceeded to the next action. With the by-dimension order, they annotated all actions for a single performance dimension at a time, and then returned to the beginning of the interaction to annotate the next dimension. The second independent variable in our study was annotation frequency. Each user in the interaction with the robot consisted of 3 photo-taking tasks, one after another. With the per-task annotation frequency, the participants annotated the robot's performance after each task was completed. This required interrupting the interaction after each task. Meanwhile, with the per-interaction annotation frequency, the participants annotated the 3 tasks after the whole interaction as completed. We had a mixed design where participants only experienced one of the annotation orders, but experienced both annotation frequencies. For our key results about the self-annotation process, we conducted surveys after each interaction of the 3 photo-taking tasks and asked the participants to indicate their perceived disruption of the annotation to the interaction, the perceived annotation difficulty, and the perceived memory burden. We also recorded their time taken for completing the annotation. We then used linear mixed model analysis to evaluate the effect of annotation order and frequency on these aspects of the self-annotation process. We first found a trend toward more disruptions to the interaction when annotating with the per-task frequency than with the per-interaction frequency. However, the per-task frequency made it significantly less challenging to remember the robot's performance than per-interaction frequency. Similarly, per-task frequency led to significantly lower annotation difficulty than per-interaction frequency. In terms of the annotation time, annotation with per interaction frequency was significantly more time-consuming than with the per task frequency, possibly because of the extra memory burden and difficulty induced by the longer slice of interaction to remember. Meanwhile, annotating with the by dimension order took significantly more time in comparison to the by action order. For our results on mapping implicit feedback to explicit performance, we considered 4 models that output a per action performance value in 1 to 7 for a single robot performance dimension. One model was a learned model based on a recurrent GRU neural network. The model was trained in a supervised manner on the mean absolute error, MAE, with respect to the per action annotations provided by the participants. We compared our GRU model with 3 baselines using random and informed guessing. We compute the MAE results averaged across all leave-one-out votes. For proficiency, the GRU model had a significantly lower error than all the baselines. For the other dimensions, our GRU model was also significantly better than the random and sample baselines. Our results show that a predictive model trained with our study data will infer the explicit feedback labels from implicit numberable reactions better than guessing, especially when considering photography proficiency dimension. Worth noting, we obtained similar mean absolute errors for the GRU model with different annotation order and frequency. This suggests that the experimental conditions did not affect the quality of the self-annotation data. To conclude this presentation, I will provide our key takeaways on how to collect high-quality implicit feedback datasets in HRI. Most importantly, the self-annotation of robot performance resulted in data that could be used to map implicit feedback to explicit performance values better than guessing. Furthermore, the way the self-annotation process took place influenced human perceptions of the self-annotation task. Thus, for future self-annotation processes, we first recommend increasing the frequency of annotations whenever possible to reduce memory burden and the annotation difficulty perceived by users. However, annotation pilots should be conducted to find a balance between the how challenging the annotation process to users and how disruptive annotating is to the interaction. Lastly, we recommend labeling all robot performance dimensions for small slices of time, for example, per robot action, and familiarizing users with the annotation process early on during data collection. This can save time, potentially reducing the cost of creating datasets of implicit human feedback in HRI. Thank you.